All right, so we've all spent time with the gas laws, right? Boyle's law, Charles's law. They're great at telling us what gases do. But have you ever stopped to wonder why they do it? Today, that's exactly what we're going to do. We're going deep, down into the microscopic world, to check out the really cool model that explains everything, the kinetic molecular theory. So think about it. We know these gas laws work. I mean, Boyle's, Charles's, the ideal gas law, they're solid. They came from tons and tons of experiments, and they perfectly predict what happens when you mess with the gas's pressure or its volume or its temperature. But they don't give you the why, you know? Why does squishing a gas into a smaller box actually make its pressure go up? And why does heating a balloon make it get bigger? That's the big question we're jumping into. Okay, so let's get into it. The answer to all our why questions comes from this really elegant idea called the kinetic molecular theory. We'll just call it KMT for short. And you can think of it as the rule book for how individual gas molecules play the game. And, what's amazing about KMT is how simple it is at its core. It basically says that all the big picture stuff we see and measure with gases, like pressure and temperature, it's all just the result of what trillions of tiny individual molecules are doing. And the whole theory, the whole shebang, really just comes down to 5 basic ideas, or postulates. So here they are, the 5 main rules. First, gas particles are always moving, constantly, randomly, and in straight lines until they hit something. Second, the particles themselves are basically just tiny points. Their actual size is so small compared to the huge amount of empty space between them that we can pretty much ignore it. Third, this is a big one, pressure. That's just what happens when these particles smack into the walls of the container. That's all it is. Fourth, when they do collide, the collisions are elastic. Think of it like perfect little billiard balls that bounce off each other and the walls without losing any speed or energy. Oh, and they don't attract or repel each other either. And finally, number 5, and you gotta remember this one because it is absolutely crucial. The average energy of their motion, their kinetic energy, is tied directly to the temperature in Kelvin. Higher temp, more energy. Simple as that. Okay, so that's the theory. But a theory is only useful if it actually explains what we see in the real world. So the big test for KMT is this. Can these 5 little rules explain the gas laws we've known about for centuries? Well, let's find out. Let's put this theory to work. First up, let's tackle a classic, Boyle's law. You remember this one? It's the one that says as you squeeze the volume down, the pressure goes up, as long as you keep the temperature steady. So how does KMT explain it? Okay, picture this. You've got some gas trapped in a cylinder with a piston you can move. Now, according to our KMT rules, the pressure inside comes from all those tiny molecules constantly smacking into the walls. So what happens if you push that piston down and shrink the volume? Well, you've just made the room smaller for all those same molecules. They're definitely going to be more crowded. And this is the why, right from the KMT playbook. Since the box is smaller, the molecules don't have to travel as far to get from one side to the other. That means they're going to hit the walls way more often. Right? And if you have more collisions happening in the same amount of time, that means more force is being applied to the walls. And we measure that increased force as higher pressure. Boom. Boyle's law explained. All right, next up, Charles's law. This is the one that connects temperature and volume. It says if you heat a gas, its volume increases as long as you let it expand to keep the pressure the same. So, how does our theory handle that? Well, this is where that super important 5th rule really shines. Remember, increasing the temperature means you're pumping up the average kinetic energy of the molecules, so they start zipping around faster, and when they hit the walls, they hit them harder. Now, wait a second. Harder, faster collisions should mean higher pressure, right? But Charles' law says the pressure has to stay the same, so what gives? How is that even possible? The answer is pretty slick. To balance out those harder hits, you have to make the hits happen less often. You have to decrease the collision frequency. And the only way to do that is to give the molecules more room to fly. By letting the volume increase, you're making the particles travel a longer path before they can smack into a wall. So you have these harder collisions, but they're happening less frequently. The 2 effects perfectly cancel each other out, and the pressure, it stays constant. It just makes sense. And you know what? The theory explains Avogadro's law just as neatly. That's the one that says if you keep pressure and temperature fixed, the more gas molecules you have, the more volume they take up. It's a direct relationship. Just think it through with the KMT rules. Let's say you start pumping more molecules into your container. What's going to happen? Well, more molecules means more things are going to be hitting the walls, which should drive the pressure up. But the rule is we have to keep the pressure the same. So how do you do it? You have to increase the volume. By making the container bigger, you give all those new molecules a larger surface area to hit. This spreads the collisions out, so the number of hits per square inch of wall stays exactly the same. It's another perfect balancing act. So look at that. We've just seen how KMT perfectly explains the big gas laws. Pretty cool, right? Now let's zoom in a little closer on that core idea, that link between energy, temperature, and how these molecules are actually moving. The big concept we need to focus on is kinetic energy, which is just a fancy term for the energy of motion. And when you look at the formula, you see it depends on two things, the mass of the particle and its speed. But here's the kicker. It depends on the square of its speed. What that means is that speed is a huge factor. Doubling a particle's speed doesn't just double its energy, it quadruples it. And this brings us right back to what I think is the most mind-blowing part of this whole theory, that fifth postulate. It tells us that temperature, the thing we feel is hot or cold, the thing we measure on a thermometer, is nothing more than a reflection of the average kinetic energy of a bunch of molecules we can't even see. It's the bridge connecting our big everyday world to the invisible, buzzing world of atoms and molecules. Okay, so if temperature is all about motion, that leads to a really fun question. Just how fast are these things moving? Are they all going the same speed? Let's pull out the molecular speedometer and take a look. Well, the truth is, it's not one single speed. In any puff of air, you've got a whole range. A few molecules are kind of loafing along, a whole bunch are cruising around an average speed, and then you have a few absolute speed demons rocketing around. This whole spread of speeds has a name, the Maxwell-Boltzmann distribution. But even though individual speeds are all over the place, for a gas at a specific temperature, the average speed stays nice and constant. So how fast are we talking? Let's make this real. The air you're breathing right now is mostly nitrogen. At a comfortable room temperature, a typical nitrogen molecule is cruising at around 519 meters per second. That doesn't sound too crazy until you convert it. That's over 1,100 miles an hour. Just let that sink in. The particles in the air all around you right now are moving faster than a fighter jet. All right, let's fit the last piece of this puzzle into place. We know that temperature locks in the average kinetic energy. But we also know that kinetic energy depends on both mass and speed. So that begs the question, how does the mass of a gas particle change how fast it moves? Here's the key. Remember our rule? At the same temperature, all gases have the same average kinetic energy. So imagine you have a balloon of helium and a balloon of argon sitting next to each other in the same room. Since they're at the same temperature, their molecules have to have the exact same average kinetic energy. No exceptions. So think about that. If a lightweight particle, like helium, has to have the same energy as a heavyweight particle like krypton, how does that work? Well, to get the same amount of oomph, the same kinetic energy, the little helium atom has to move incredibly fast. The big, heavy krypton atom, on the other hand, can just lumber along at a much slower speed and still have the same energy. So it's a simple trade-off. At the same temperature, the lighter the molecule, the faster it has to move. And this isn't just some abstract concept, you've seen this in real life. This is the whole reason behind something called Graham's law of effusion. Since light gas molecules move so much faster, they're way more likely to find a tiny hole and escape. It's exactly why a helium balloon goes flat so much quicker than a regular balloon filled with air. Those tiny, zippy helium atoms just find their way out way, way faster. So there you have it, the kinetic molecular theory. With just 5 simple rules, it gives us this incredible power to understand why gases do what they do. It connects the world we can see and measure to this invisible, chaotic dance of molecules moving at supersonic speeds. But there's a catch. KMT is a model for ideal gases. It assumes the molecules are just points and that they never interact with each other. And that leads to the final question I want to leave you with. What happens in the real world when you crank up the pressure or drop the temperature and those simple rules start to bend and break? Well, that's when things get really interesting.